All right. So we have now talked about continuations, delimited continuations, and first-class continuations. I'm not going to spend much more time talking about, like, here's all the fancy things you can do with first-class continuations, because again, I feel like Haskell programmers are actually probably most equipped to already know that there are nice, useful things you can do with these, like implementing, exceptions, state. You can use it to implement coroutines. You can use them to implement, like logic T-like things. But this raises the question of why would you want to do this with delimited continuations, given that we already have monad transformers to do it? And the answer is essentially just performance, but that raises the question of how do we actually implement these things? And that brings us to this last point, which are native first-class continuations. So it might seem like this is a complicated thing to implement because, again, we're taking a portion of the executing program, reifying it as a function, which, again, we've just been talking about in this syntactic way, but that sounds really complicated, and it seems really slow. One thing that we could do is we could use continuation passing style, which is, if you use some kind of CPS monad, then you can explicitly thread the continuation through the computation as a lambda, and then you can just at any point say, well, give it, hand me that lambda. And so there are monads that have implemented this in the past, and so technically, the work that I did recently did not bring delimited continuations to Haskell, because you could always have used delimited continuations. But this is fairly slow, or it can have significant overhead, and if you're interested, I gave a talk about that 3 years ago at ZuriHack, and you can watch that talk. A nicer way to do it is to bake them into the runtime, because surprisingly, despite this being a super high-level idea, there's actually a really efficient implementation that's not very complicated of delimited continuations. So in order to understand what that looks like, we can take a look at just some hypothetical continuation here, and there's another way to look at it, which is like this. We can divide it into a sequence of nested continuations like we did before, but now they're sort of minimal in that you can't divide each of these anymore, right? They're sort of the smallest sliver of a continuation, and they're all nested inside of each other. And we can call these individual sort of continuation slices a continuation frame. So any continuation can be decomposed into a sequence of nested continuation frames. And what does this look like? Stack. A stack. This is a call stack. This is indeed, has a very direct correspondence with the actual call stack that, say, GHC or some other compiler uses to represent where you are in your program. And I mean, this is actually a good way of thinking about it intuitively, that the call stack keeps track of what's left to do in your program. So the call stack is the continuation, which is kind of cool. So if we imagine some kind of like abstract machine, and now we're gonna, for the first time in this talk about some actual operational details of some machine here, where the Redux is this control operation, and the stack looks like this, then what actually happens? All we have to do is walk the stack to find the prompt. So we'll start with this frame, say that's not the prompt, look at this frame, that's not the prompt. Here we found the prompt, and so now these frames highlighted in red, all we have to do is copy them into the heap. So we have now literally taken these stack frames, copied them into the heap, we removed them from the stack, and then we also removed the prompt from the stack. And now we continue execution by replacing that control operation with G applied to some heap object, which I'll call cont here, which contains a pointer to those heap allocated stack frames. And that's it. That's all we have to do to implement continuation. Now, of course, the question is what happens when we apply that continuation, because now it's a function, right? So this is a special function. To the programmer, it just looks like an ordinary function, but to the runtime, it's a special function represented by this chunk of stack frames. And so then when we apply it, say to this string hello, then we just do the process in reverse. We just take these frames, we copy them back onto the stack, and then we continue execution from there. And that is the entire implementation of delimited continuations, which, as if you've been paying attention, is literally just memcopy. And memcopy, okay, so you might say, well, memcopy, it's linear time in the size of the stack frames that we're copying, which is true. But keep in mind that even though we're illustrating it like the code itself is contained inside the stacks, you might say, well, what if I have some really big program? Then this would be very expensive. But keep in mind that each frame is really only storing a pointer to that bit of code. It's not actually containing the code. So each one of those frames just corresponds to the nesting depth of the expression. So in reality, a lot of the time, this is just, a few words. And what that means is that, computers are really good at doing block copies of a few words. So in practice, this turns out to be remarkably cheap. Now, of course, there are pathological cases where maybe it's more expensive. And so, there are ways to optimize that. And if it turns out that people hit performance pathologies. We can maybe take a look at that. But remarkably, and this super high-level operation just corresponds to this very, very low-level operation, which I think is kind of neat, and is actually, I think, one of the best arguments for languages should have delimited continuations, because they're not that hard to implement, and they give you a lot of control over this very low-level operational detail. Yeah, pun not intended, actually. All right, so we have now covered continuations, delimited continuations, first-class continuations, native first-class delimited continuations, and that's really it. Now, of course, there's a few things that I want to mention, a few miscellaneous details that I've sort of glossed over a little bit. So you can optimize this further if there's particular assumptions you know about how the continuations will be used. So for example, in OCaml, they didn't just implement what I've described here. They implemented one-shot delimited continuations, which is to say, I guess they're not linear, they're affine, where you can only resume from that point 0 or 1 time, not multiple times. And the advantage of this is that you can optimize it so that you don't do as many copies, right? You're just sort of swapping a stack in and out of what you're currently running, but you don't have to be actually copying things around. And so they're using that to implement sort of user programmable thread schedulers, because that turns out to be, if you're just kind of yielding from a thread and then resuming it later, then you can represent that way. And, of course, this is something that if it turns out people want to do in Haskell, we could add operations to have sort of a special first-class continuation. Maybe we could even use linear types to help with that. So also, obviously, I have been talking about this sort of strict pseudo-Haskell, and Haskell is lazy. So in the real operations we have, they all live in I/O, or really, state hash, which is the implementation of I/O, and that allows us to have predictable ordering and a predictable continuation in a lazy language. What this does mean, though, is that you can't, for example, copy or capture the continuation across like a use of unsafe perform I/O. Because once you do that, you're going into lazy code, and then the order in which things are evaluated is not well defined, and so the continuation is not well defined. So we have some restrictions on how they're used in Haskell, but as long as you're working monadically, then you can do this, which corresponds, I think, intuitively to in the past, if you wanted to get continuations, you would use some monad. So the interface hasn't really changed. And of course, in reality, it's not just memcopy. There are a few other minor details that we had to worry about in GHC, but they really were quite minor. And it's really remarkable how how small the patch was to implement this. And really the most complicated thing was really just getting, if you're capturing a continuation, and that means you're unwinding the stack, and you manipulated the asynchronous exception masking states, then we have to save and restore that, and that is a little bit more complex.